So I decided to title my talk "The Good, the Bad, the Ugly," because in some sense, one of the things you can do after spending so many years doing functional language, you realize some things that are good and some things that are not so good, and then something that are outright ugly. So hopefully we'll get some of that. And I have to apologize, I actually probably infringe on some copyright here because I like that. The movie is wonderful, so if you haven't seen it, you probably should see it. I did take the screenshot of the movie poster. I will start with a little bit of the context of the talk because to some extent you probably don't, coming from the background I have spent my life in here now for a long chunk of it. However, I also give you the history of how this functional language came about. In particular, since in 1984, I took my first computer science course. Sorry, I'm lying, my second. My second computer science course was a compiler course, taught by two individuals, Augustsson and now I went back. Johnson, thank you. And they talked about this functional language stuff. And I thought to myself, fortunately I didn't say it loud to them, but I thought these were the biggest nutcases I've ever encountered. We know that this is just nonsense. Embarrassing enough, 10 years later, I was reading the papers backwards and forwards and backwards and forwards and said, oh, how did they do that? And implemented the same thing. So I had to eat my words there. Anyway, so the context. I'm coming from a design environment. I'm going to talk to some extent from the Intel environment. And what happens there is, of course, that an idea needs to be implemented somehow. So in typical textbook way, we all know that waterflow software development and hardware development always happens, and it works just fine. You start with the architects that takes the idea and sort of say, okay, how are we going to build these things? The microarchitects then refines that into actually what's going to look like, the RTL level, the register transfer line description of it with the microarchitecture. Are you going to have caches? How big are the caches going to be? What type of cache you're going to have? You're going to have a reorder buffer, and so on and so forth. Then you have the design engineers that get these tasks from the microarchitects and say, well, how are you actually going to build it? And then you get the mask designers that they get down to the really nitty-gritty details, how do you lay it out, and so on and so forth. And then you have the test engineers in the end that's going to test whether the whole thing's going to work, and so on and so forth. And you create a whole bunch of different artifacts along the way, and you do a lot of validation that they are all the same. Now, of course, as you already realized, that's not really what happens in practice. So we start with the same picture, but what actually happens is because the architects have their own little ideas. They like, oh, I like this. Well, that actually makes sense in the context of an audience. It's a very different story. So they'll start driving the project in this direction because they like that application. They like this idea, like the Pentium 4 architect liked the idea of having an execution unit that ran at twice the frequency. So if you bought the Pentium 4, it had the execution unit running twice as fast as the rest of the processor. So when you bought the 3 gigahertz Pentium 4, you had a 6 gigahertz core running inside. That didn't necessarily mean that it was a good processor, but it was the architect liked that. The microarchitect is trying to rein them in a bit and tell them, of course, well, that doesn't work, and they try to get closer. The design engineer just does more of this. They continue driving each other, and so on and so forth. And, well, one thing happens, of course, and you start iterating the feedback loop. There's lots of iteration. If it's only between two of them, that sort of kind of works. The problem is, of course, sometimes it's over multiple. Someone discovers, by the time you get to the design engineer, discover this is not possible to do in the time for the time you've given me or the cycles you've given me, and they have to go back to the architect, and the architect says, well, yeah, maybe. Okay. Typically, I have to give up my idea. No, I don't want to. Anyway, they continue this, and then, of course, then the sales team comes in, and they decide to repaint the target to say, this is a great success. That's an important one. And in all of this, of course, that takes many, many years. A typical design process at Intel would take four-ish year, and it still started from something that was already a processor, so it was never starting from scratch. You also, of course, had somewhere between 300 and 800 people working on it for the whole time, not counting all the support personnel and so on and so forth. So there's a lot of people, a lot of time working for a long time. And in all of this, of course, you do a lot of validation. And two types of validation. You check that what you captured is what you intended, That's kind of important. But then, of course, you want to make sure you don't introduce bugs along the way. So that's another part you need to do. So how does the VOS and FL come around in all this context? So once upon a time, or in 1990, which for most of you is before you were born, at least many of you, I came in from, just finished a postdoc, and had a nice little nifty C implementation of a new verification technology, a new model check technology called symbolic trajectory evaluation. Very highly tuned, was really good, I felt very good. Worked on very large circuit with almost 100 gates or 100 flops. In fact, I think I even did 1,000, which was way more than anyone else could do, I claimed. At the same time, there was also this general purpose theorem prover called Hall. And it just so happened that there was a professor at UBC that had spent his PhD on doing Hall, verifying processors. Fortunately, the day I was giving my interview talk there, I found out in the morning, because I had breakfast with an old friend, that he sort of mentioned just as I was leaving, oh, by the way, you know that Jeff Joyce is at the UBC? And I was like, oops. I better take off my first slide in my interview talk, because it says, these guys that do theorem proving are really idiots. I took that off, and maybe that's why I got the job. So we looked at each other for about 6 months, eyeing each other rather suspiciously. He thought that I didn't do formal stuff, because I was just using BDDs and things like that. There was no logic here. There was no pure logic. And I thought he was an idiot. To put a point, that just he works on toy examples. These are toy processors. The 8-bit processor does sequential code. Come on. However, we did get a long flight back once, and we did in these days we would probably have been kicked off and banned from flying, because we were arguing and fighting for the whole 4 hours on that flight. But it was probably good, because we actually realized, oh, actually we have different parts of this answer to the story. Because I can really handle large circuits, but I do miss the verification, what I'm actually verifying in the end. He can say what you verify, but he can't really work on big things. So maybe combine the two is the idea. So use the SD as a decision procedure for Hall. So we just need to send expressions from Hall down to the simulator somehow. Simulator should run and get answers back. What can be hard about that? Well, Hall expressions were really functions. They were just functions. We need a way of evaluate functions. Functions with Boolean variables in them. Okay, so how about some way, how do you evaluate function? Well, that's a functional language, effectively. Okay, let's make a little language. That was the birth of FL. Then, of course, reality came. We tried to use it. Yeah, we had a demo. However, it was really cumbersome to use, because think of it as you're driving a car, but instead of driving the car, you're sitting on top of the roof in a chair with a rope, as Mr. Bean would have shown you how to do. You sort of pull in one thing, yeah, eventually the car turns to the right, but it takes a little while, and you don't really have any control over it, and feels very, very awkward. It's a lot easier if you go down and sit in the steering wheel and actually drive the car directly. And that's sort of the realization here, too. It was a lot easier to do all the work by FL directly. And so maybe as time went on, the whole part became less and less important, less and less useful, and providing less and less value. So now, at the same time, once you start using FL, you realize very quickly that, oh, if I just have a typo, it crashes. It core dumps. Well, why? Well, you have a typo. How do we fix typos? You have a type checker. So we threw a type checker in it, and then as time went on, it became a full language. Functional languages are very easy to build. Deceptively easy to build, because the small core is never enough. You will always add a little bit more and add a little bit more. And then you see a nice idea from some other place, you add that too. So it continues to grow. In fact, it has grown for 25 years. Now, this became very powerful. And as John said, we could actually verify things. And then Intel lost $470 million, which is about today is almost $750 million. And of course, they said never again. So they decided, oh, let's invite a couple of professors to spend the summer. They'll entice them. So I and a couple others were invited. And of course, they were not quite up front what the goal was. I didn't realize it until afterwards that this was, of course, an interview. It was a 3-month interview. And they, of course, rolled out the red carpet. It was a wonderful summer. It was nice. Everything was very wonderful. And I got to use it on real hardware. It was kind of fun to do it and see what worked and what didn't work. So I decided to stay. And so 21 years at Intel later, and now 2 or 3 years here at Chalmers, the system has continued. And in effect, 4 phases of FL. And I think it's interesting to follow that history a little bit. Because it sort of tells you a little bit how it all came about. So we started as a scripting and implementation language. And to make this a little bit more lively, I will actually try to give a demo of this, at least in the first part of it. So the first stage here, the first stage we're talking about, I'm just going to run an FL session here, and hopefully you can see it. So contrary to most languages, we have BDDs and set solver variables built into the language, so you can just declare variables. Here, declare a bunch of them, and you can write expressions like not of A or not of B. That's not very interesting. You can evaluate it, and the BDDs gets evaluated. Everything of type bool is a BDD underneath the hood here. You can also write the Morgan's law if you like. Oops, that was not in the wrong place. You can write the Morgan's law, and you will see that if you evaluate x2, it actually looks the same, even though there are 2 different expressions. Big as it gets. Sorry. That's even bigger. Try that. Oh dear. These are difficult real-time questions. Let's see. Can we try some E4 maybe? I don't even know whether that's going to work. So real-time attempt. Better? Amazing. First test. Same thing again. Now, of course, you don't want to print them out every time when you compare. So you may want to say it's the same, is 2 expressions identical, 2 BDDs the same. But that's only good for certain things. Maybe you want to say, when are they the same? So we have 2 equality operators, the equal, and the equal operation. Here, equal again. But the equal operation is say, under what condition is the first expression equal to the other? Or if you like, when are they not equal? And if you look at that, you say, that looks like A is true and B is false and C is false, then they're not equal. And of course, you can make a substitution to make sure that is the case. Now, these are, of course, trivial examples. When you have expressions that have, say, 400 variables in it, and an expression that takes 200 pages to this is very useful to be able to ask questions. Is it true that this is not equal? Or like this one, for instance, here's a quick question. Does example 3 imply example 2 or example 1? Well, one has to think about this. But of course, I don't ever just do this. Yes, it does. In general, having a Boolean calculator is very, very useful. To show you a little bit more advanced, do a model checker. Suppose you have a little state machine. I just created one little visualization of something. It's not quite the state machine, but it's sort of gives you an idea of the state machine looking at. You can go from state 0 to 1, back to all. You can stay 1, you can go to, and there's another bunch of states 3 and 4 here. And we can just describe a little state machine in a trivial way. So what we actually did here, there, we build a transition relation that says 2 sets of variables, the current and the next state variables, and we simply say it's a predicate that says whether you can go from that state to that state. Now, if you want a reachability state machine, so if you want to look at the transition relation, yeah, there we go. Not really what you like to see. So we'll ignore that. So that's how I do a forward search. Well, you essentially have a predicate that says what it is, and you say, okay, take the current set of states you're in, conjunct it with a transition relation, quantify out all the current state variables, and then change from the new state to the old state variables, and that gives you a new set. The state's the image of the current state set. You order that in, or you join the union with the current state set, And then what do you do then? Well, you continue this. What does that mean? Well, in functional language, you recurse. And we just simply do continue the recursion until we have the same identical. Since we can compare functions, we do an equal, and we stop at one point. So here we have, what is it? 1, 2, 3, 4, 5, 6, 7, 8 line, at least for reachability. And if you want to see if this works, let's start with the initial state. There's 0 and see what are all the states we can reach. Here I also enumerated them, how they look like. And it says you can reach state 0, 1, 2, and 5. And if you look at the picture, that looks kind of right, doesn't it? Can I get this one too? There we go. If we start from 0, we can go here, we can go there. The thing we cannot go into 3 or 4. And indeed, they said we couldn't get to that. So, and of course, if you just want the same thing, but you pre-image instead, same thing, just slightly different versions of the quantifications. And you can do here, started from, say, if you want final state being, what is a final state? 3. If our final state is 3, where could you have been before? What are the set of states that will eventually get you to 3? Well, it turns out to be only 3 and 4. And similarly, if you want to do the same for 5, it turns out you could have been in any other state. Good? So that gives you sort of what this allows you to do fairly quickly in the system as a scripting and implementation language. At least give you an idea. Of course, we wrote large number of lines of code for equivalence verification and property verification. There's large number of libraries for these things, but it was all written in FL. Now, one thing that happened at this point, we started realizing not only is it good for scripting and describing things and asking queries and debugging things, but it turned out to be a really nice specification language. So we're going to spend a deep dive into that a bit later in the talk. So let me come back to that. But effectively, adding these booleans into the language turns out to be a very, very effective way of describing specification for what you want it to do, what the system should do. And we're going to see a lot more of that. However, remember, oops, we're just going to skip this. Let's go there. And remember, we had the Hall-Voss system, where we had a theorem prover and a model checker together. Well, that was not very useful, I claimed. Go back, showing you too much. But it did show us one thing, because when you have a large verification task, model checker will never do it. Model checker has never the capacity to do what you actually need to do, at least in industrial circuits. You will always have to break down your property into a collection of a large number of smaller properties. The problem with that is that these are not interesting properties. To verify that the collection of properties actually imply what you think it implies is largely tedious. It's a large amount of small, gory details, which means that it's absolutely horrible for people to do, and they will guarantee to get it wrong. So you need some mechanization to prove those things, to do right things. So you kind of do need a theorem prover to combine your results. At the same time, you want the model checker to do as much as it possibly can. So we said, what you actually need is not a full-blown theorem prover. You need an idiot savant theorem prover, something that's just good at doing combining results. So we created, effectively, in the standard way, you define a data type for your expressions and everything else. You wrote a little theorem prover in the LCF style, theorem proving style. And one of the decision rules was, of course, execute to evaluate, run the ST, run the model checker, and to get results back. That sort of worked. It was easy to use, but you ended up with this extra layer of interpretation. You sort of have to write things, and then the ST wasn't run directly. It was run on you had to interpret the data type to run it. Cumbersome, and the worst part, whenever you just realize you need something new, you have to sort of walk over all of your code to add new data types and the pattern matching and everything else. It was very cumbersome to extend it. So the trick there was, of course, to introduce reflection to FL. So instead of just having FL can now FL programs. So one of the things with reflection, of course, you can say eval. So you can now reason about the FL program, your spec is your FL program, you reason about it, and at some point you say, okay, now I think what I've reasoned about is something that FL can evaluate and execute, and just get the answer, click, evaluate it. So you effectively have a theorem prover that at any point in time can say, okay, evaluate as one of the decisions. It turns out to be a very, very effective way of doing a theorem prover and still have clean things in there and actually fairly efficient. The nice part is that if you don't want to do theorem proving, you don't see any overhead at all. You run the model checker naked, you do all the things you want to do. The reasoning about it, it comes later when you want to put it together. And without putting any extra overhead on the end user, which has turned out to be a very valuable thing. Now, the fourth phase, and this is now spread over 20 years, we start writing actually hardware descriptions in this language. And let me show you part of this, because the previous talk we listened to had something that was somewhat interesting related to this, or actually very interesting and very related also. Because one of the things we heard was that visualization is kind of needed. And turns out you really need that. So let me just go to a slightly different example here. Now, can I, well, here you probably don't need to see as much. So we had this hardware description language. We can describe types. I'm not going to talk about the details, but what I want to show you is more important. Because when you build a circuit, what you actually want is visualization in your design. And visualizing circuits turns out to be something that's really, really valuable. Let's do this full screen, so hopefully you can see. So this was a small little circuit that just decided, goes through, reads from memory, reads the first data, reads the second data, does some computation according to instruction. Actually, it either adds or subtracts it, the data, and writes it back. So it's a tiny little microprocessor. What I wanted to show here, though, is that what comes out as you design this is this visualization immediately. So being able to visualize a circuit as you design it, you can look at the text for this whole thing, and you will discover very quickly that this is really cumbersome to see. Did I connect everything? Did I write the right name? These are still very small circuits. It's very easy to make a mistake. You throw it into visualization, and you can almost immediately see, oh, I connected to these things completely wrong, or I used the wrong thing here. You see it sort of absolutely instantaneously. Now, it's not a correctness proof, but it's a bit like type checking. Visualization is sort of, type checking does the obvious things, you connect the things that are wrong type to each other. Visualization takes the next step of showing, does it look like what you think it should look like, what you had in your head? Very, very valuable. And of course, if you have these, you want to do other things. For instance, you have a state machine, you want to see the state machine, how it behaved and so on and so forth, because after all, the state machine is not a box with flops and so on and so forth and some next state functions. It's like that. It's states that you move from one to the other. You want to be able to see that. It's very hard to understand it otherwise. And of course, if you have this and you say, okay, the next thing I want to see is, of course, I want to also describe behaviors. So in the time-honored tradition of functional languages, we describe a small domain-specific language embedded in here for describing waveforms. So now you can run the whole thing in your wonderful here, and you can say, let's look at the node browser here and get to the inputs. Let's just show you what we have here. Did we not run it? No, we didn't run it. Well, that's helps if you actually run the simulation. It's a lot more to of course, then you get values. Big deal. That's useful to see. You can share this, you look at the waveform, put a timeline there. More importantly, you can say the values. I want to back annotate them onto the circuit so you can see what's going on in the circuit, and I can single step through here and see what happens in there. But of course, I really want to see the state machines not as this, but I really like to see the state machine moving. So let's go there. You can actually see what the state machine is doing in the current state. Very, very valuable to trying to understand. Because the biggest thing to do in hardware design is actually understand what you captured, not anything else. And I think this actually applies to almost any other domain as well. So rather than giving more circuit description, let's go and talk and dive in a little bit on how to use FL. So here's an example. And I decided to do a little bit of very recent work. just to sort of give you an idea how I operate in this system nowadays. Now I'm going to show you. So hopefully you will follow most of it. Some of it will be maybe a little bit rough around the edges. I'll warn you in advance. But what we wanted to do was the following. Suppose you have some things that generates data coming in. Data, of course, is typically noisy, but it has certain behaviors. What we actually had was data recorded from buses at Volvo, speed and engine speed, and it was just time series recorded. They had actually 15 years of recordings. That's a lot of data there. And we were using it for machine learning, but actually the problem was we had no labels. We didn't know what this was supposed to be. At the same time, we also knew that we were interested in certain behaviors. We wanted to describe, okay, we want a cycle here where you warm up first, and then you do three iterations of accelerate, drive for a certain speed, slow down. To describe this, we want to find out how many of them were available that did those kind of things. So how do you write a spec for something like this? Well, what we did was something very simple. We described a data type first, of course. How do you describe a waveform or a time series? Well, a value is either steady, or it has a slope, or it's one sequence followed by another sequence, or possibly the conditional. It's either this or that, depending on some condition, or it's a repetition. Very small, little, tiny little data type for describing waveforms. Then, of course, we want to do a DSL to write this concisely in FL. So what we did, we described a whole bunch of overloaded functions. We used a lot of fixity declarations, and FL actually has a lot of binders and fixities added to make DSLs very convenient, or embedded DSLs, I should say. So you can actually change the syntax at your leisure, and you can change almost anything to make it look reasonably nice. So now you can write this, which I think is reasonably nice. It says that it's 0 for 20 seconds, then it goes from 0 to 20 during 10 seconds. You can argue with my choice of words, but then to 20 to 100 in 5 seconds. So it slows up, it increases slowly first and then much faster, and then stays 100 for 10 seconds, and then goes down to 0 again. And then repeat it twice, and then there's some 0 afterwards. That's a pretty clean one. And actually, what you can do now is, of course, and the whole idea of embedded DSLs is, of course, you want to be able to extend it to other user extensible functions. So here I did a little extension where I want exponential decays. Typically, signals don't just follow a ramp up or down. They exponentially decay very often. So I wrote a little function that effectively says, if you have one time unit only, there's not much to do. If you have two, you have a midpoint and so on and so forth. And it figures out what the function should be. What I'm using here is currently, I think, 1 minus exponential 3 up to the 3 times the ratio. So we get to from 0 to 99.9 or 98%, something like that, in essentially the limit. Just pick them. Thank you. Okay, now you can write the same thing, but now you can have exponential decay also in there. Of course, this is just describing something, not very useful still. So what you may want to do is you may want to say, okay, I want to actually take this and now generate a time series that give me essentially a list of values for, let's say, 400 time units. What values could that signal take on? So to do that, we write a function called duration. One thing that looks suspicious here, and I didn't talk about it, is that notice that I'm just saying duration. I say get duration for this follows. You get the duration of the first one, you add it to the duration of the second one. Now, I didn't point it out, but actually these are not integers. These are bit vectors. They store them internally as arbitrary precision integers, arbitrary precision bit vectors, I should say, which means that we can do symbolic computation later. But for the time being, think of it just as integers. They're not quite that much different. Then to get the value at a certain time, well, if you're in the steady state and the time you're asking for is within the duration, well, that's the value. Otherwise, it's 0. And continue. If it's a slope, you just compute how far are you in the slope. So t over duration times the difference between the end value and the starting value plus the starting value. And if it follows, then you will use the duration to determine if are you in the first sequence or in the second sequence. That's nothing deep or profound here. And for repetition, you just do recursion. You unroll it. If I'm within the first, if the count is 0, then you're done. Otherwise, you get the value, unrolling it once, and repeat the process. Nothing strange there. So once you have that, you can also say, okay, if I want take one of these atom, I call them atoms for some reason, you can make a sequence that says how many cycles in the maximum time, and it just generates a BV list, or int list if you think of that. So take the first example and then put a little visualization on there. Again, remember I said visualization. You can get this waveform. As I said, we start in the beginning with a slow ramp and then faster ramp. Well, you can see it in the waveform, at least if you squint a little bit. And the more advanced one with exponential ramp actually looks like exponential ramps. That looks pretty nice. Now the interesting thing, and what makes it actually worthwhile doing, is that these can also be symbolic. So here I declare a bunch of symbolic variables. So T1, T2 for different time points, or time durations, and a count that's also symbolic, and a new variable called warm-up. And then I say certain constraints about them. So the T1 and T2 are both greater than 5. T1 is strictly less than T2, and both T1 and T1 is less than 30. And the count is between 0 and 3, inclusive. Now, we can take the same, we can write the formula that looks like this. If it's warm-up, then we do this duration, this sequence, otherwise nothing. So either you do a warm-up or you don't do a warm-up. And then follow that by something that's going to be iterated count number of times. And count, again, is symbolic. It might be 0, 1, 2, or 3. So if you do all of this, you can run exactly the same code as before, add them to sequence. But instead of now getting 0 normal values, first of all, it doesn't take a fraction of a second. It takes 2 minutes a little bit to get it. Not on my laptop, I should say. It's not on the big machine here. And it generates a BDD of 36,000 nodes. And actually, what the interesting thing is, it actually represents 8,000 different waveforms. In one single symbolic list here, we have actually 8,000 different waveforms encoded. And this is the whole point. Because now I can do the visualization that randomly picks values of those 8,000 and visualize them. So notice what here randomly picked some. The first one did actually warm up, followed by 2 iterations of it. The next one did not do a warm up, but did 2. The third one, no warm up, but it did only 1. And the next one is warm up, followed by 3 iterations, and so on and so forth. So this gives you a way of very concisely describe, symbolically encode very large number of examples. So you can now test things. Suppose you have a recorded data, or if you want to label them. How many of them, or under what condition is one of these tests that you give it an encoding for it? Can you find variable assignments to your symbolic encoded so that they match this one within a tolerance? But obviously, they're not going to be identical because they have noise in the real data. So now we say, if you are within a delta, so how do we see that? Well, we are essentially going through it and testing it. And if the value of the symbolic minus the time value that you got, if the absolute value of that is less than delta, then you could add that conjunction to the remaining. So if a test sequence comes back and says false, that means that there is no assignment to the symbolic to make it look like that test case. But a lot of cases, of course, it will come back and say something more interesting. So here we took the first test and says, under what condition do they meet? And it turns out that, well, it had to have a warm-up and it had to have a count to be 0. Well, so actually not the test I showed on the waveform, unfortunately, on the previous slide. But in this case, the tests were a couple of hundreds that I ran. And you can also ask interesting things like, are the values that are forced in the BDD here that you must have for it to be satisfying? And of course, more interesting than this is not for a single individual test, but here's one where I took all the tests and I just saw how many are these covered. I ordered them together to see how many of all possible symbolic specification tests have you actually covered by your tests. Well, it turns out that you have covered quite a lot, but what's interesting, if you ask for forcing of the covered, you will discover that the count 1 has to be must be false. So if you think about this a little bit more carefully, There are no time zeros in a test that had a pattern repeated 2 or 3 times. So this is not the test set that I showed on the previous slide. But this one had no count 2 and 3, which I actually didn't know. And the reason for not knowing it, you would think, well, you have a test, there's just a lot of data. You don't really want to look at data all that often. So, why? Well, I think, of course, you can use it as a specification like we did in formal verification. This can be a spec, what you're interested in to verify that your implementation, say, satisfies, does the right thing for these things. You can check if an explicit test satisfies the spec. We show that. You can characterize collections of tests. You can generate interesting tests for corner cases. This is an interesting one, but because in general it's not easy to generate corner cases that have certain properties. You may want to have a property that says, oh, I want to have odd number of repetitions of this with an exponential decay on that, and no warm-up or something like that. You can do something like that and say, well, give me a test for that. And the reason for this doing it was actually we're trying to have a way of creating labels for unlabeled data. So effectively, we're going to take our data set and we're going to run it and say, okay, can we uniquely determine a label for each of them? So we can get a fairly good first approximation. You can actually run it as your decision procedure for something, but this is probably almost certainly too slow. So we want to just label data and then train a neural network for it as a machine learning. Plus, of course, we want the generalization that the neural network provides for us. And then, of course, one could imagine doing existing training augmentation using this. So, in summary, so what was good about it? Well, it turns out to be very useful. It could handle a lot of things. It grew as it needed to grow. The idea of incorporating the Boolean variables into the language turned out to be a stroke of blind luck. I would like to claim I was a genius that did that, but unfortunately I was not. It just turned out to be a very useful thing to do. And I think we have just scratched the surface on this one. Being able to use it for all these things, that's definitely good. Functional languages are really good for these things. Good. The bad. Well, I'll be honest, FL is not a fast language. It's not meant to be fast. It wasn't intended to be fast. It has become fairly good performance, but that's largely because a lot of the infrastructure you rely on, like map and fold and so on and so forth, are implemented in C code inside the graph reduction engine. So the actual interpreter itself is in C, and so you can actually move code from FL into the C world if you're willing to live with the careful garbage collection issues that you have to deal with. However, that is not precisely safe from correctness each point of view. You can still end up, if you make a mistake, and discover that you core dump when you don't want to core dump. And the flexibility is, of course, doubtful. We try to be very hard-nosed about it, so only implement primitives that could be used rather than implement solutions. We had a version of VOS that was taken over by a group in Haifa. They didn't take that. They implemented solutions, and the code base bloated greatly, and about 4 or 5 years later, it basically had to be thrown away, and we went back to a version that had smaller primitives and built more in FL. The mixture of FL and TickleTK code in the GUI is painful. I have to say, I have yet to find a good visualization tool building environment in functional languages. I really wish I could, because anyone who's used TickleTK knows that scar tissues are horribly and deep. And particularly if you use the language that has strong type checking, and then you go to something that it doesn't even change the syntax. It doesn't even check the syntax, so you can do all kinds of horrible things. The ugly. Well, anyone that has done embedded domain-specific languages know that error reporting is less than ideal. Let's put it that way. Infinite type. Yeah, what I did was I forgot a comma. That's not precisely obvious. Here, the type checker couldn't resolve the overloaded types. Well, it turns out that you declared an arbitrary internal var that you didn't use, the foo. That's not what I would call a descriptive error message. So, what did we learn? Well, I think there was a nice unified environment that works extremely useful. There's a natural fit between the type of task we did here in the functional language world of looking at things. And it provides a new capability. I think that's really, I used to say, I coined it the Carl's law, a new language will be successful if and only if it provides a new capability. If you just do it because it looks nicer, it seems cleaner, it's shorter, you're not going to succeed. You provide a new capability that is not provided by anyone else, you will win. The classical example for me is that Perl. Who would here in this audience vote that Perl has the best syntax have you ever encountered? So why was Perl is Perl so incredibly successful? Well, because it solves a problem that nothing else solved before. And I think that applies to any language. So, however, let me also finish off with a plug. For the first time in my life, I can actually say VOS is now open sourced. I've rewritten, of course, the VOS that sits in Intel, I couldn't take with me. So 20 years, or as my wife used to say, our fourth child is still stuck at Intel, and I could not take it with me. However, that meant that I spent the last 2 years re-implementing a lot of things. Fortunately, I was lucky. I got the version of VOS that I took with me into Intel. I managed to find that. A friend of mine at UBC decided to tar up my directory when I left UBC, and 22 years later, he sent me an email. I hear that you're in academia. Would you like the source code of everything you did? I owe Mark a lot. So I have basically made it now. Actually, it's better than the internal, because second time you can do things you couldn't do otherwise. So if you're interested in playing with it, please do. And I would love to hear you doing something neat and interesting about it. Thank you very much.
So we have time for 1 or 2 questions.
So my question is, as you are creating more of this new language, were you sort of inspired by, for example, Prolog, where you have similar cases of checking logical values and so on?
Was I inspired by Prolog, for instance, when I did the new language? Not necessarily. I take inspiration from almost anywhere. I tend to be problem-driven, though. I tend to, I was trying to solve a problem, and I use whatever hammer, screwdriver, wrench, whatever I have available. I write code in a lot of different languages. I tend to use whatever I can available. I have used Prolog on things. I find Prolog very difficult to use, but that's mostly because I didn't use it enough to be really. It's sort of like, yeah, it's a tool that I know about, but it's down in my toolbox so deep down that I don't think I really know how to use it, which is probably a problem for me more than anything else. I probably should have. In general, I find that working on the problem first, come up with a solution, and then I go and read the literature, discover what they did and how I can improve what I did. It works really, really well, mostly because then I know why they say that in the paper. In the paper it says, oh, by the way, we did this decision. And you know, when you read the paper the first time, you say, what? Why? Once you implement yourself, you realize, oh, that's what they meant by that sentence. Now I understand. So actually having hands on and having your hands dirty is, that's how I work. It's not good if you're trying to get a PhD done, because it takes a long time and a lot of hours of work. But it does allow you to understand your problem better.
A question about your BDD implementation in FL.
Yep.
When you have two BDDs for the same function, is that the same object or is it 2 objects?
It's
how do you know when to release the BDDs from memory?
Yeah, okay, so 2 questions there. The BDD is, of course, written in C internally, and it uses a standard cons hashing. So 2 expressions evaluate to the same BDD if they are the same, and that, of course, internally is done by sharing the pointer. So the equal function is a trivial operation. It's a pointer equality only. The garbage collection is actually why I actually built this new language, as opposed to just take Haskell and just put a BDD package in it. It's actually quite hard to get garbage collectors to collaborate nicely. And the problem here is you have to garbage collect the FL heap before you garbage collect the BDD, because FL has lots of pointers into the BDD package that are now dead. You don't want to garbage collect the BDD package when you have dead pointers into it. So they have to actually interact with each other in rather subtle ways. And a lot of the engineering here was actually get that to work well. It's not hard to get it to work. To work well is hard. So there is a fair amount of work in the system of making sure the garbage collection happen at the right time in the right way, and so on and so forth. And then on top of that, BDDs of course have dynamic reordering on top of things, everything else. So that also happens in all these things. So you have to really play games here. But yes, that's part of it.
So this looks like the language that came out of demand for something new, which is always good. But when doing something new, how many times, like, did you just build on top of it all the time, or did you discard big pieces of it and like redesign? And if so, what were the like pitfalls that you like threw away?
I've actually rewritten the language 3-4 times, not entirely, but good chunks of it 3 or 4 times. Actually, the individual components, I'm a firm believer in throwing away and rewrite scratch many times. You have to. There is no other way. The code base is about 50K of C code, so it's not that big for all the things you actually get out of this. And that partly is because they've been thrown away. Unfortunately, the version now that's in open source is not as clean as it should have been, because the number of cleanup happens inside Intel. And I already told you I can't take it with me. I will probably rewrite the front end again. That's probably the one that has the ugliest code. The separation, mostly because the VOS 2 you see here does not have reflection. Well, it is there, but I'm not documenting it and not showing it. Because the parse and front end needs to be fixed before you can have good reflection. You get a reflection today, but it's so ugly because partially the pattern matching gets compiled during parse time and things like that. You don't want that. That needs to be fixed up and cleaned up. So I've rewritten many things several times. It's sort of inevitable. Sometimes they get better. The biggest danger is always the second system syndrome. Oh, now I'm going to fix this, this, and this. Oh, and by the way, I should add this, this, and this too. Bad idea. You should fix this and this, but you should not do this until you've done that. And I fail as often as everyone else.
Okay, I think we must bring
Yep.
the session to a close now.
Yep.
Thank you again, Colin.
Thank you. Thank you.